I'm glad to say this is the 69th Theoretical Physics Colloquium, and we will have Professor Martin Savage from the Institute for Nuclear Theory at the University of Washington. He got his PhD in 1990 from California Institute of Technology. He had several postdoctoral positions at Rutgers University, University of California, San Diego, Carnegie. Actually, that was it. Then he got a faculty position at Carnegie Mellon University in 93. And he moved to the University of Washington in 96. He is a full professor from about 2003. He is also a senior fellow at the Institute for Nuclear Theory since 2013. Over the years, he received many different awards and honors. I will not be able to list them all, but let me mention at least a couple of them. And that includes the SSC Fellow in 92-93, DOE Outstanding Junior Investigator 95-97, Fellow of the American Physical Society since 2002, IBM Faculty Award in 2012, Humboldt Foundation Research Award in 2012, and since 2019 until now, he's a member of the Washington State Academy of Science. He also did a lot of different professional service over the years, for example, serving as an associate editor for Nuclear Physics A during 99, 2010, editorial board of Physical Review C, 2012, 2015. He served on scientific board. Actually, he is serving right now on the scientific board of ECT Star in Trento, Italy. Over the years, he also was very active in the DNP of the American Physical Society and many other things. His research interests include many aspects of nuclear physics, quantum simulations of lattice field theories, lattice gauge theory, effective field theory for nuclear physics, entanglement in many-body systems, and strong interactions. And today he's going to talk about towards quantum simulations for nuclear and particle physics. And with that, I'll give the microphone to Martin.
Thank you very much, Igor. That was a very, very nice introduction. Yeah, so thank you very much. It's a pleasure to be here. Thanks for the invitation, Igor. I'm going to talk about the progress we're making towards and the grand vision for quantum simulations for nuclear and particle physics. And let me start by saying that we're at a really kind of remarkable time with regard to computing and simulation in these areas, and of course, more generally in other areas. During the last 5 years, we've seen two disruptive technologies enter our fields. One is quantum computing, which is going to be the focus of today's colloquium. And quantum computing, the motivation for this is very strong. It was first suggested in the early 1980s as being required for the calculations of quantum systems. And this allows us to address features of quantum systems of importance for NP and HEP that are inaccessible through classical computing. And the power of this new technology is through the control of entanglement and coherence. These are properties of quantum mechanics that were somewhat viewed as peculiarities of quantum mechanics in the 20th century, but are now becoming the tools that are going to allow us to make significant progress going forward. The second is machine learning. So this is also another disruptive technology that's entered during the last few years and allows us to make predictions from learning correlations. Particular, for instance, one generates, for instance, training sets. One has an algorithm to learn the correlations and learn, in fact, about correlations that are far smaller and more complex than we can visualize ourselves, and then use these to make predictions for other things. As I said, I'm going to be focusing on quantum computing. During the last year or so, the last 5 years, but during the last year in particular, there's been dramatic increases in funding for the development and advancement of quantum computing for a number of reasons, including communication and various other important elements, and also quantum simulation itself We expect that quantum simulations of materials, biological systems, and so forth are going to be just as important as they are for making progress in HEP and NP. So in 2019, it was a remarkable year. There was a real shift in the development and evolution of computing itself. It was the year where the first demonstration of a quantum advantage was accomplished for any particular type of computation. In this case, it was for a computer science type computation. So the Google was able to perform a computation of quantum random circuits in a matter of hours that was demonstrated to take days on classical computing hardware that's available. It was performed on their Sycamore chip, a 54-qubit superconducting device with sort of sophisticated communication between the qubits. This was, of course, not an event that came out of the vacuum. This built upon decades of research and close collaboration between universities, national laboratories, and technology companies, and was certainly not the singular architecture that's going to take us forward. It's one of multiple architectures. For instance, in addition to the superconducting devices, there's trapped ion systems and Rydberg atom systems that are also being developed and demonstrating similar capabilities. Of course, they have different attributes. But this just happened 2 years ago. And so we're now searching for a quantum advantage for scientific applications, including in the area of nuclear physics and high energy physics. So I entered this area of research around about 2016, 2017. And that was for a number of reasons. Firstly, the community had just completed its activities in understanding exascale resource requirements for classical computing to address the important problems both in NP, HEP, and across the other domain sciences. And there was classes of problems that require beyond exascale computing resources in order to accomplish the precision and also address also address some of the observables that are important. It also coincided with the first appearances of quantum devices available to scientists through the cloud or sort of building upon the infrastructure that was being developed at universities and national labs. So this meant that scientists such as myself and you were able to access quantum devices to begin to try out and learn how to develop quantum circuits with a goal of trying to perform computations of observables, at least at some point in the future, that were beyond what one could do classically. So these are termed NISQ era devices. NISQ stands for noisy intermediate scale quantum. These are systems of a few physical qubits where there is no, sorry.
Hardware, not software, but hardware.
Well, so there's both actually. So there's the devices became available, but on top of that, in order to control the devices and perform the computations you would like, there's also a software stack that sits on top of these that in particular the technology companies have developed, like IBM and Rigetti. And a typical mode of access for through the cloud is by lightweight Python scripts and then submitting sequences of quantum operations through the cloud into the queue for these devices. So it was both accessible to hardware, but also the fact that there was a software, an easy access through software made this also possible. Icarus, does that address your point? Okay.
Thank you, understand now, thank you.
Yeah, okay, thanks. So we expect to be in this era for near-term future, where the devices are not ideal, they're noisy, and this is always going to be the case. But at the moment and for the near term, they're without error correction. And so one should view operating these devices as performing experiments as opposed to performing input and output from your laptop. So at the fundamental level, the reason we have great optimism for able to solve our problems, right, ranging from Planck scale type problems through subnucleon scale problems through to astrophysical, is the fact that quantum mechanics works the same at all the scales that we've probed experimentally. That is, one then has the attributes with the advances that are expected, one has then the attributes to be able to use the rules of quantum mechanics in laboratory scale and laptop scale devices in the same way that the rules of nature operate at these large scales and the very small scales. And so this was, of course, the vision of Feynman and Benioff, Manin, and others from the early 1980s. And it was pursuing that vision, both broad-based advances in engineering, physics, quantum information, that's brought us to where we are today. So here's a graph that Dave Wecker showed a number of years ago at an INT meeting for quantum computing and nuclear theory, and it's very informative and captures much of the vision, and that is, if one imagines the calculational time it requires to perform, to determine the ground state energy of a complex molecule with some level of precision, for instance, 1 part in a million, how that computational time scales with the number of atoms in that molecule, then one finds with classical computing this will grow exponentially, asymptotically. And while with the quantum computing, with an ideal quantum computer, one expects this to scale with polynomially with the number of atoms. And so where we are today is, of course, classical computing is able to do remarkable computations for some of these molecules. This scheme runs out of capability once one gets to a certain size. And at some point, there's going to be a crossover where quantum computing is going to be necessary in order to get the precision that is required as one increases the number of atoms. And so, for instance, with a 100-qubit device, which is where we are today within factors, then one's able to address for the first time problems in chemistry that are beyond classical computing. And if you ask about the dimensionality of the Hilbert space with 50 qubits, then this corresponds to requiring around about 20 petabytes of classical computing memory, which was the current leadership computing classical capabilities or size of memory around about 2 to 3 years ago. And with 300 qubits, one has a Hilbert space of dimensionality of more states than there are atoms in the universe. With 300, you're around 10 to the 90, and the atoms in the universe is around 10 to the 86. And so we're on a trajectory to rapidly hit these markers. This, as I already mentioned, in 2019, calculations on 50 qubit devices were already accomplished, demonstrating a quantum advantage, and 100 qubits is certainly near-term accessible. So where to look for a quantum advantage? And this is obviously a complicated question, and it depends on the particular area that you're interested in. But one of the things to keep in mind here is if part of the computation or the computation can be done efficiently on the classical computer or even inefficiently on a quantum computer at the size that you need, then you don't need a quantum device to actually do it. And so the quantum devices should be used, at least in the near term and intermediate term, most likely, to address the parts of the problems with the classical computers can't solve, which means that we actually have to know our problems and understand how to break them up into the pieces that are amenable to classical computing resources today or near term, and the parts that are not, but can be addressed with a quantum device. And we're only at the very earliest stages of making this dissection of the problems, and leads, of course, naturally to hybrid architectures, and considering hybrid architectures as opposed to considering architectures that are just completely quantum. Those devices will actually not exist, as they'll always be. Any quantum device will be hooked in through classical computers, particularly at the level of controls, but also at the level of input and output and so forth. So thinking about hybrid architectures is really the thing to have in mind. And so then thinking about how we take our problems and split them and then reconnect them later on is certainly paramount. So I have a couple of slides, and well, 3 or 4 slides, and just to outline the areas where we think quantum simulation is going to provide an advantage. So firstly, real-time dynamics and highly inelastic particle production. So in the context, for instance, of lattice simulations of quantum field theories, then of course, one of the big targets has always been quantum chromodynamics in the electroweak sector, and also low energy effective field theories for nuclear physics. There are known limitations with classical computing for quantum chromodynamics, particularly real-time dynamics is something that's essentially inaccessible with at scale and with precision, and also finite density computations, as I'll talk about on the next slide. But and one is able to look at low energy reactions, elastic or essentially elastic, but with small inelasticities. But to explore directly fragmentation and highly inelastic processes is well beyond what can be accomplished with classical computing. It's expected that, and of course, these explorations and investigations are, of course, only at their earlier stages, but it's expected that aspects of fragmentation and highly inelastic processes, in particular S matrix for these, can actually be addressable. So another area is, of course, finite density systems. In classical computing in Euclidean space, these such calculations in general suffer from sign problems. There are particular instances where that's not the case, particular values of coupling constants in effective field theories, or particular sets of quantum numbers. But in general, for instance, a finite baryon number, there's a sign problem one encounters with the stochastic sampling. With the Hamiltonian formulation, as is going to be implemented in quantum simulation and quantum devices, such limitations are absent. Of course, it still remains to be demonstrated that there remains to be demonstrated that such calculations can be done, but this is certainly an area of active research, and there's results in one dimensional field theories with chemical potentials that exhibit sign problems that in fact have been shown to be amenable. And I'll mention that briefly later on. Also, from the high-energy physics side of things, one would like to be able to explore with precision the production of baryons in the early universe. This is obviously a non-equilibrium process, and which is also expected to be amenable to quantum simulation. In more nuclear physics settings, then one of the interesting areas where there's been recent progress is in the evolution of neutrino flavors in extreme astrophysical environments, in particular in supernova, where the evolution of neutrino flavors also depends on the neutrino flavors themselves. It's the physics is that the neutrinos through the electroweak interaction are coupling to the differences in lepton numbers, and so as a result, neutrinos interact with neutrinos in a forward coherent process, and their evolution depends on in a nonlinear way. This has been known for a long time, of course, The quantum simulation offers the possibility that, in fact, these dynamics can be addressed with precision at scale. And there's been a number of works, as I'll show you later on, that is moving forward the area in this area. Electroweak processes, again, something related to the experimental program, for instance, DUNE, where one has neutrinos impacting a nucleus, and we're giving rise to an inelastic process. And so this is also something that's remarkably complicated and doesn't scale well on classical computers to get to the precision that we need. Whereas with quantum simulation, one expects to be able to address these problems with precision at some point in the future. And then also there's low energy nuclear reactions for similar reasons, and also the larger scale collective processes such as fission. The fact that with a quantum system, as I mentioned on the earlier slide, about the fact that the dimensionality of the Hilbert space that one can address scales exponentially with the number of qubits, means that the quantum many-body problems with large numbers of bodies can be potentially addressed on such devices in a way that just can't be done with classical computing. And so it's expected that we'll be able to perform precision calculations of the structure interactions of medium and large nuclei, nuclei that can't be addressed with the required precision at scale with classical computers. And I'll have some more comments about the behavior of these Hilbert spaces later on. So the 20th century, from the high energy physics point of view, was in some ways half about chasing short distance fundamental interactions, looking for the Lagrange density, the unification of forces that was suggested in many arenas to occur at short distances. Of course, it was a remarkably successful venture, with the standard model being incredibly robust and predictive. It was also about developing non-perturbative techniques for numerical simulations of quantum chromodynamics at long distances, where perturbation theory fails, but lattice QCD has been developed and has been shown to successfully be applied and provide the necessary predictions for high energy physics observables for in particular, for instance, in electroweak processes, but also a number of other arenas, including beyond the standard model physics. And so we saw modeling in high energy physics give way to controlled effective field theories, where lattice QCD should be viewed as a low energy effective field theory also. And the leading order wave functions, or the states that one accomplishes, perturms one builds around leading order, or for lattice QCD at the short distance structure, is separable at leading order. And so the initial states that one starts with are separable. They're tensor products. So for instance, in heavy quark effective theory, the leading order is a tensor product of a heavy quark with the light degrees of freedom. And then one has a systematic way of including corrections through perturbation theory. And in nuclear physics, there was, in particular in low energy nuclear physics, it was about the short distance physics again, in particular handling the repulsive core of the nuclear-nucleon interaction and high body interactions. And there's a period where it looked like the short range interaction meant it was intractable. Computing the properties of larger scale systems were intractable. The field was reinvigorated by the introduction from high energy physics of the renormalization group and effective field theory, and also techniques used in chemistry for many body problems. And so again, the modeling gave way to controlled effective field theories and precise phenomenological interactions that have now led to remarkable progress in making reliable predictions for complex nuclei. Now, the 21st century, for both HEP and NP, the open challenge here is the quantum correlations and the non-locality. And so this is these areas are essential for furthering our understanding of the emergent systems from our fundamental theories, but also in understanding how to perform quantum simulations and using quantum computers. So this is currently where a big challenge is right in front of us. So let me skip that. I want to mention just some work that I did with Carolyn Robin and Natalie Pillay. And this gets to the heart of one of the comments I made earlier about hybrid computation. And that is, if you look at light nuclei, then of course entanglement and how we perform computations depends on the basis. This is of course not new to anybody, but one can show that the quantum correlations can be organized through self-consistent computations in such a way to diagonalize the problem into spaces that need to go to the quantum devices for precision computation and scale, and then parts of the problem that can be done on the classical compute part of the hardware, and then brought together to solve the problem. And so here's one example where, for instance, if one uses a harmonic oscillator base for single particle wave functions, and then you compute the mutual information, the orbital mutual information and the negativity, then you see that there's strong connection between particular sets of orbitals that extends sort of within shells, but also extends to much higher orbitals. And by self-consistently including two-body interactions and rebuilding the single particle orbits and then asking the same question, then you can see that the correlations are now much more confined into a limited space, and the negativity by construction effect in this method vanishes. Which means that in this case, the mutual information contains, and there's a spelling mistake, mutual information contains both classical and quantum correlations, and the negativity is entirely quantum correlations. So the techniques that we've been have been developed in the field over the last many decades are directly relevant to understanding how we can efficiently use the newly emerging quantum devices. There's also some work that we're involved in with regard to symmetries and entanglement, and in particular in the two nucleon sector, one can ask about the behavior of strong interactions at low energies. And one can show that, in fact, nature is very close to the point where the S matrix, in fact, wants to preserve the entanglement between the initial and final state. It doesn't want it. The probabilities of changing that are small. And so these correspond to points of spin flavor symmetry. And so what one's seeing here is that there's a connection now between the suppression of fluctuations of entanglement and symmetries that can be identified in the Hamiltonian. These are not symmetries of QCD, these are emergent symmetries. And this is part of just a general feature, and is something that will be certainly an area for exploration going forward. There was also work on the numerical side, in particular work by Dean Lee and collaborators, that have shown that where one has these enhanced regions of enhanced symmetry, one suppresses sign problems in the classical computation. And so one then sees that there's a connection now between the ability to perform classical computations and the suppression of fluctuations of entanglement. And so this is just beginning to, this is just sort of a start to understand how understanding entanglement in our problems and the symmetries they're connected to can actually help with classical computing. So I want to talk about complexity just a little bit. And so there's a wonderful article by Scott Aronson from a number of years ago in Scientific American that outlined complexity classes, particularly for scientists that typically aren't used to thinking about complexity. And so the complexity classes indicate that for a generic set of couplings, for instance, in a particular system or a generic system, the scaling of resources, of computing resources as the system becomes larger and larger. And so, for instance, problems that can be solved efficiently on a classical computer reside in P, polynomial scaling. Problems that lie in NP are problems that can have solutions that can be verified in polynomial time on a classical computer, and so on. On the quantum side, the assignment of problems and understanding is also quite advanced. Excuse me. And so, for instance, one has BQP. So these are bounded error polynomial scaling quantum resources. So problems that lie in BQP are problems that can be addressed efficiently on a quantum computer. We haven't, as a field, really understood where our problems reside here, except there's a number of exceptions to that. One is one understands finding the ground state of a K-local Hamiltonian, that is Hamiltonian with 2-body, 3-body, 4-body interactions, sits outside of BQP typically. That's for generic sets of couplings in the Hamiltonian. But interacting lattice scalar field theory, including with external classical fields, sits inside BQP, and in fact, it's BQP complete, which means that any other problem that can be solved efficiently on a quantum device can be mapped with polynomial resources onto an interacting lattice scalar field theory, and in particular onto computations of the S matrix elements. And so one of the questions to ask is, should complexity be a limitation? So if one understands that your problem generically sits outside of BQP, should you not pursue it? And the answer really is, should complexity be a limitation? And the answer is not until it is. And so, for instance, on this diagram, imagine you have a problem that actually sits in QMA outside of BQP. And as the quantum chemists have recognized, it's important to understand the coefficients in front of these different scaling functions, for instance. So one can imagine that a polynomial scaling like x to the 10 compared to an exponential function, but with a small argument, one can make significant, this polynomial is worse. And in fact, this exponential is much better behaved until you get to about x of 9,000. And vice versa. And so the complexity classes indicate the worst case. And in fact, the problems can be much more benign in scaling, in particular where we are now in the near term with modest devices. We're not close to asymptotically large quantum resources. No problem is out of bounds. And it's important for us to pursue effectively, essentially all of them. It's also the case that the B in BQP provides us with latitude. And the B means bounded. So one's going to specify observables, particular observables of interest to HEP and NP with a particular error. So one might need to know some quantity with some precision, say 10 to the minus 4, which means you have latitude now to actually change the theory that you're simulating in a small way, as long as it's less than roughly 10 to the minus 4. And so this then gives us an opportunity to in fact, solve a different theory that may be much more amenable to simulation, and then perturbatively correct it in a way that can move us closer to the actual result. So how do you map one's problem? It's easy to say that we have a problem that we want to solve on a quantum computer, but how do you actually go about doing that? And so again, there's been, over the last several decades, there's been a number of important results obtained. So one is time evolution through tritorization has been shown to lie within BQP. It's efficient for quantum devices. And so one expects that if you have n quantum degrees of freedom that are locally interacting, and you want to have them evolve forward for some time t, then one can efficiently simulate this with n degrees of freedom through n time steps, n discrete time steps, with a resource requirement of n times t operations. And even with fermions, this doesn't change that situation dramatically. The scaling goes from n to some polynomial in n. it's also the case that d-dimensional systems are optimally simulated with d-dimensional systems. You know, just like biological systems that map where the brain map of the system is intrinsically the same topology and layout as the system itself, it's been shown to be efficient for two-dimensional systems to simulate two-dimensional systems, but inefficient, for instance, for a two-dimensional system to simulate a three-dimensional system. So in HEP and NP, we're interested in simulating, of course, in 3 dimensions. And so we're going to be looking to use and ultimately, to ultimately use, but develop algorithms and technology to actually use 3-dimensional quantum systems, because that is how it's going to scale efficiently going forward. So this sort of brings us to the whole area of co-design. I mean, if it was the case that one could simulate 3-dimensional systems with a 1-dimensional quantum device efficiently, that would probably be the path to pursue. But the fact that it's not means that we will have to be thinking about designing devices that are appropriate for our problems. So now for quantum field theories, where are we and how are we thinking about these things? We're going to be wanting to simulate on a 3-dimensional lattice, which means we're going to be distributing the discrete Hilbert space in a way that is hopefully optimal or approaching optimal for our calculations. So one of the ways one can do this is defining the fields on the sites of the lattice and then generating a discrete Hilbert space by assigning qubits there, and then just doing this on a regular space-time lattice, sort of a somewhat of a straightforward extension of what one does classical computing for quantum field theory. This is not unique, and of course there's other suggestions, for instance, looking at a uniform distribution of qubits and then using the renormalization group to map onto the problems that we want to solve. It's yet to be demonstrated that this will actually work, but conceptually it should work. One needs to understand then how to map the fields onto these discrete Hilbert spaces, which boundary conditions you're going to use, and then understanding which part you're going to perform on the quantum device and which part you're going to perform on the classical computer. And I'll give an example of that in a little bit. So the different mappings, I already mentioned, it's important to explore all mappings. There are no clear winners at this point, and it's far too early. One can think about having explicit gauge degrees of freedom. In 1D, you can have them both present or you can integrate them out. One needs to understand about how to implement and enforce Gauss's law, particularly how does one implement error correction. So there's a lot of development that remains to be done. We're just scraping the surface. Then one has to, of course, you're looking for simulations where you have a complete control and quantification of the uncertainties. This is something that's well understood from classical computing. Here we have additional places where systematic errors are introduced, particularly dealing with implementing continuous variable systems on discrete Hilbert spaces. But there's also progress in that arena. So the gold standard for quantum field theory is scalar field theory. This is work by Jordan, Lee, and Preskal, where they showed from beginning to end with control of the systematic errors, how one can start from a non-interacting scalar field with isolated Gaussian wave packets, adiabatically evolve the system to an interacting theory, have the wave packets collide, and then measure the fluxes and the particles entering detectors that are in the simulation. And so this is the gold standard, as I said. And when we were looking to do QCD and Yang-Mills gauge theories, then this is we need to, and there's been recent progress actually out of Waterloo in showing how to do an analogous analysis of these simulations. And there's a very nice talk by Nicholas Mueller recently at an ICOS workshop on summarizing the simulation strategies for scalar field theory. I'm running out of time, so let me skip some of these. Excuse me. So one of the systems that has proven fruitful and will continue to be an important to explore for quantum simulation is the Schwinger model. So this is one-dimensional quantum electrodynamics. It is something one can solve with impressive precision with a classical computer, and it's also amenable to analysis, to simulation on present-day NISQ devices, and has provided some very nice demonstrations. The first computation on a quantum device was in 2016 out of the Innsbruck group with trapped ions, where they looked at a 4-site system and showed the time evolution of pairs popping in and out of the vacuum. The continuum Lagrange density is here at the top left, and one can include a theta term. It exhibits charge screening, confinement, and also has a non-zero fermion condensate. These are features shared with QCD. From a more nuclear physics point of view, it's also interesting in the fact that it contains bound states. So there's a 2-body bound state in this theory. And there's also a 3-body system that's exponentially close to threshold. So we can also study effective, if you like, in quotes, hadronic type of processes in this theory. And here's a summary chart of some of the work that's been doing, and I apologize because there's been a significant amount of effort here and I can't summarize all of it. There's the initial work from Innsbruck in 2016. This was then replicated on the IBM superconducting devices by a team led by Oak Ridge that we were involved in. There was work on larger scale systems for understanding hybrid algorithms such as VQE for identifying ground states of this theory. There was work led by Zura Davudi at Maryland, understanding how to improve the time evolution through algorithmic improvements. And then there was also work, more recent work out of Stony Brook and Brookhaven that moving more towards the distinct, utilizing the distinct quantum features of these systems. And that is looking at time dependence. For instance, one has the theta term, as I showed you on the previous slide, and one changes the theta term and asks what happens to that system. It's obviously a non-equilibrium dynamics here. And what's shown is the vector current as a function of time. And so this is a classical simulation of what one expects to see on a device. And you see that, in fact, one's expecting to be able to compute with precision the time dependence of such a evolution. And there's also work with a non-zero theta term looking for the vacuum. This is something that, at least at scale in QCD, has a sign problem because in Euclidean space, the theta term has an I in front of it. And they were able to show that in simulations that, in fact, this should be accessible to quantum simulation somewhat easily. There's also work looking at scale and developing the analog of the JLP analysis for scalar field theory, the resource requirements for performing simulations in the lattice Schwinger model at scale. This was by Alex Shaw, Pavel Lugovsky, Jesse Stryker, and Nathan Webb. In addition to the activities related to digital simulation, there's also parallel efforts in analog simulation, and I just want to have a couple of slides on this. There's one that's particularly interesting in the fact that it sort of is somewhat new, at least in my mind, in the thinking on with regard to quantum field theories, and that is using these quantum circuits. It's been shown in this paper and of course a series of other very nice works on how to use these quantum circuits to perform simulations in the lattice Sine-Gordon model and also lattice conformal field theory. And so the lattice Sine-Gordon model obviously maps nicely into the Schwinger model, as I mentioned before. Perhaps at least a little more somewhat addressing a bit more fundamental problems in some sense as the lattice conformal field theory, because then one's able to look at the behavior of entanglement and including distillable entanglement in massless non-interacting scalar field theory on such devices. And there's significantly important reasons to actually pursue that. There's also development of analog simulations or movement towards it with SRF cavities. This is work that's being performed at the national labs, including Livermore Fermilab and also JLab. And the goal here is to, this is clearly a hybrid type of architecture where there's a significant amount of classical processing that's required to reliably determine the behavior of the pulses that are sent into the cavities to perform unitary transformations between the levels in the cavities. And so these are effectively QDITs, d-dimensional Hilbert spaces. And as I'll show you in a little bit, these may be particularly amenable for simulations of QCD. But they're also, the demonstrations so far have been related to elements of low energy nuclear reactions. There's also been remarkable progress on the control of Rydberg systems and trapped ion systems, and I certainly don't have time to discuss them all. These systems, there's efforts to bring up lattice quantum field theories, including Yang-Mills theories. On these devices also, there's been pioneering work on the theoretical side by Zohar, Serac, Resnick, and others in demonstrating what one has to do in order to simulate field theories on these devices. And this is a slide that Federica Soraci showed at the ICUS workshop recently. And so they're making good progress in Rydberg systems to stand up quantum link models. And so they have some results on small systems and are able to look at how well Gauss's law is satisfied and potential errors that will be encountered in these systems. And I encourage you to look at in more detail at her presentation and papers. So I want to say some words on QCD and lattice field theory in QCD. So the first discussion really of how to perform a quantum simulation of Yang-Mills was by Burns and Yamamoto back in 2006. And there's been a substantial progress and work since then, notably coming out of groups in Europe mainly, but also in the US more recently. I mentioned the Zohar Serac paper on actual implementation on optical systems. At the end of the day, the layout, for instance, the idea is one has issue 3 spaces at each of the lattice sites, just as one does in lattice QCD, where there's fermions for QCD, and then there's parallel transporters and links between them. The framework is, of course, built upon the Kogut-Susskind Hamiltonian. And so for just considering Yang-Mills now, that each of the links, there's going to be a finite dimensional Hilbert space. So for instance, you might have organized things in such a way, there's say 3 qubits and 3 qubits, or more generally n qubits and n qubits assigned to this link. And that allows you to then describe with the right identification the dimensionality of issue 3 irreducible representations, the number of up indices and the number of down indices. One can keep the orientation in gauge space if you like, which was the original Burns Yamamoto. You can integrate out the gauge space at each vertex, as suggested by Banuels and Carl Janssen and collaborators, and also something we did in issue 2. But then at the end of the day, the wave function that's sitting on this quantum register is a wave function in terms of amplitudes for irreducible representations of issue 3 at each of these links connecting the sites. So to be more specific here, if you don't integrate out the local sites, then one has a state vector for each of the IREPs that has orientations on the right space, orientations on the left space, and then also the dimensionality of the IREP. By integrating these out, you collapse this down and reduce dramatically the number of qubits that are required to do this. There's, of course, Clebsch-Gordonary that has to be evaluated for issue 2. One's familiar with the Clebsch-Gordonary issue 3. It's more complicated. It's still well known. And it was shown that, in fact, the evaluation of such Clebsch-Gordons on a quantum device lies within BQP, which means it can be done efficiently. And this was done by Bacon, Tron, Harrow in 2006. One has to enforce Gauss's law by hand. So first computations of issue 3 were performed. This is by my student Anthony Cavarella, Natalie Clough, who's now at Caltech, and myself, using IBM devices. And the simplest thing one can imagine is evolving a single plaquette of issue 3 forward in time after some initial preparation. And so this was done with a finite truncated Hilbert space in issue 3. And so some early benchmarks were then established that can then be used to look at the performance of future devices with regard to Yang-Mills theories. And I'm running out of time impressively here. So let me just say a few more words here. In order to actually make this go to take this type of simulation to scale, there's a significant amount of classical processing that has to happen. And in particular, if you count the number of physical states you have now just with one plaquette, one is looking at around about 2 million with a cutoff of the 24-dimensional IRAP. And the number of matrix elements that have to be computed is around 24 million. And so these are computations that will have to be done classically. This is not a big number for large-scale computing, but one sees the growth of the classical requirements as one goes to scale. There's been interesting work in issue 2, in particular, a number of calculations, one using the D-wave to perform time evolution, and there's also computations here using IBM for issue 2 in 1 dimension. And in fact, there's been an identification of the ground state of the system and also of the first excitation, the meson above the vacuum. So this is work that is coming out of Waterloo and Toronto. There's a lot of value in studying spin systems, in particular, the features that we're interested in or need to understand in quantum field theories are largely contained in spin systems. And so there's some really nice work from last year coming out of Caltech, where in a one-dimensional spin system, one is able to prepare kinks, and then the kinks are then collide. And so for particular values of the parameters, there's no inelasticities. And so what's shown here in the left panel is the evolution of the entanglement entropy as a function of time as these kinks move through each other backwards and forwards. And one sees that in fact there's non-trivial time evolution of the entanglement as a function of time. And then when one turns on a three-body interaction, then in fact one has the possibility, and one sees now inelasticities and the production of ballistic particles traveling on the light cone. So this is obviously gives us very good insights, or starting to give us insights into the dealing with fragmentation in hadrons. Okay, so I'm going to skip a number of things here. So one of the, and so there's been a number of developments, and as I said, I can't do justice to what's going on. The field is on fire at the moment. One of the interesting developments with regard to nuclear physics and low energy effective theories is on trapped ion systems. There's been work, Zora Dawoodi and Mohammed Hafizi and Pagano and collaborators looking at developing ways to have fundamental three-body interactions in the simulations, and they've come up a way with of doing this, basically extending the analysis of the derivation of Molnar-Sorensen interactions, the two-body gates. So they were able to show how, through sequence of pulses, one's able to generate a three-body interaction, for instance, of the form that looks like sigma plus, sigma plus, sigma plus. So one hopes that this can be used certainly in spin systems, but also in developing, say, looking at the behavior of three nucleon systems. So this is, again, an example where of co-design directly related for, in this case, nuclear physics. So going back to, I have a slide here that addresses or sort of points to Icarus's comment, and that is that the fact that technology companies made lightweight software available to the community to start using the devices was critically important. There is essentially no barrier to anybody entering this field with regard to writing code to perform simple computations on these devices. And there's a large number of inbuilt functions that are very helpful, including the translation between, for instance, a gate-based for a superconducting system, and then also moving and generating the circuit relevant to be applied for trapped ion systems and using the Mollmann-Sorensen gates. And so here's just an example. For instance, if one can input a circuit for IBM and then easily translate through, for instance, Circ or the Circ software to generate a circuit relevant for trapped ion systems. And I don't have time for that. I do want to, well, actually, one of the remarkable, some of the remarkable progress in the last 12 months has been with regard to error correction. Even 2 years ago, it wasn't something that was really talked about for the near term, but there's been advances, particularly by the technology companies, building upon the work out of labs and universities, where now one's seen demonstrations of exponential suppression of errors using, in this case, the repetition code by Google using their Sycamore QPU, where you can show that you have, it's certainly known, for instance, in the surface code and repetition code and others, you expect exponential suppression of errors as you increase the size of the number of qubits defining your logical qubit, but using the repetition code, they're actually now a first demonstration of this. It's also the case that for color codes, work come by Honeywell, in fact, shown and demonstrated the first elements of implementing a logical qubit using a color code. It is also the case that in the previous work by Google, they demonstrated the ability to detect errors with a surface code. So they are on the way for implementing a logical qubit through a surface code. So let me just close here. So, we're really in a remarkable period with regard to computing generally, but also with regard to developments for simulations relevant to high energy physics and nuclear physics, both from quantum field theories and quantum many-body systems. And in this presentation, I just talked about aspects relevant for quantum field theories. One can address previously inaccessible phenomena, non-equilibrium dynamics, highly elastic processes, structure of large nuclei, neutrinos, and dense systems, when the quantum devices become available, robust, and sufficient fidelity. And the NQI centers that were sent up that I mentioned very early on are there to bring the scientists, computer scientists, and all of the engineers together in co-designing and developing various aspects of the quantum infrastructure. And so with regard to nuclear and particle physics, it's clear that we have very specific problems. There are different problems between NP and HEP, and there are different problems to condensed matter, although they sort of sit under the same umbrella as this second bullet point. And so to solve our problems, we're going to need to work together, and this has of course already been recognized and is already happening in designing quantum simulators and quantum computers with the appropriate architectures and attributes. And the new frontier really here, both from an analytic point of view, a simulation point of view, and just sort of a theory development point of view, is in quantum correlations, entanglement, and simulation. So thank you very much.
Thank you very much, Martin, for a nice presentation. Now we'll have some time for questions. So everybody in the audience, if you have any questions, please raise the hand and we will go in the order of those. Okay, I don't see any hands yet. So let me break the ice and start with a very, very naive and simple question. So in some problems, there are the so-called butterfly effects when something little changes, brings big effects over the time evolution. Is this the type of problem that quantum computing would help with, or it's sort of unclear?
So, yeah, so great question. My guess, the thing to keep in mind is that not all problems are going to be amenable to quantum computing, right? So there's going to be a large range of problems that are not going to scale well. Things where a small error propagates exponentially through the simulation are going to be remarkably troublesome to simulate and will generally lie outside of what a quantum device can do unless there's some advance in understanding how to actually put it onto the device. So typically problems like that, where a small perturbation, the initial condition leads to some exponential divergence, that part is not going to be unchanged by a quantum device.
I see. Thank you. Okay, next question, Bernd Müller.
Hi, Martin. Thanks for this very nice general overview of where quantum computing can help in nuclear and particle physics. When I think about the 20th century developments, one of the important ones, especially for nuclear physics, as you pointed out, was the development of effective field theory approaches in various contexts. How do you see the relationship or the synergy between effective field theories and quantum computing? Are they mutually supportive of it? Does quantum computing possibly replace the EFT technique in certain cases? How do you see that?
Yeah, so that's a great question. And so some of the discussion with regard to the complexity classes sort of touches on that, and I just gave us a slight snippet. But one of the challenges really is going to be for quantum computing is to be able to develop, effective theories, and I'll use that broadly defined, where the leading order is now entangled and can be put onto the device efficiently. And so just, in the 20th century, we came up with effective field theories. We then put these onto classical computers and we were able to make progress non-perturbatively, for instance, lattice QCD. The challenge here, and I only sort of have one known example here, is to understand leading order that's entangled that can be put onto the device and then solved and then solved efficiently, and then perturbations built in around that around that leading order configuration. So that's something that remains a theoretical challenge. And I'm not sure whether it sits under the umbrella of effective field theories. I think it's sort of a generalization, but identifying non-local leading order wave functions, if you like, as starting points is a significant theoretical challenge for us. But that's going to be important for sort of breaking and developing approximations to let us use quantum computers to address some problems that are intrinsically at scale intractable, if that makes sense.
Yeah, no, I think that makes a lot of sense. That would allow you to use the quantum computing for aspects where it is absolutely necessary, rather than doing part of the calculation that you can also do in traditional ways.
Yeah, exactly, yes. But that's a big challenge for theorists, is to understand how to build those, right? All of us have developed and been educated in understanding operator product expansions and local expansions and multiple expansions and their effective field theory incarnations. But developing understanding how to think about non-local systems is something that we really haven't been trained to do. We're just sort of grappling with that.
Thank you.
Okay, next question is Jean-Francois Paquet. I hope I pronounced that correctly.
Yes. So you mentioned that other fields, of course, are interested in quantum computing, including condensed matter. What's your feeling about the status of where the nuclear physics community stand compared to other fields? Are we ahead? Are we roughly in the back?
Yeah, so that's something that's a really good question to ask. So the quantum chemists seem to have been ahead of the curve here for a number of years before HEP and NP came in. The problems in the condensed matter physics resemble under the, at the 10,000 foot level are the same problems. They're the non-equilibrium dynamics, and there's the finite, those types of problems. And there's techniques there, right? And those techniques have been built on the techniques that were developed in classical computing. So so they have a tool set, and our community is learning rapidly from their developments. We have different problems. So, and this has always been the case, that the algorithms that are being developed for instance, quantum chemistry, they're, conceptually advances, but we have different forces, right? So while, those algorithms work optimally, for instance, in chemistry, the concepts are brought into NP, but then we have to develop our own. So I don't think I'm sort of shy from saying more advanced than not advanced.
Fair enough.
There's different problems. It's certainly the case that within quantum information, there is so much understanding and development, formal development, that we have to bring in. We need to work with people in these areas and the other domain sciences to address this efficiently. There's a language barrier a little bit. For instance, harmonic chains are the same as quantum field theories. Who knew? It took a while to figure that one out. And so when you search for things, you miss things. But there's a lot of technology and techniques that are out there that we still have to integrate into our things.
Okay, thank you.
Okay. Any other questions from the audience?
Can I ask a question here?
Go ahead, please.
Oh, okay. I mean, first enjoy that, but it helps me so much to learn here and think about here. It's really enjoy that, but therefore I ask only not deep questions, but the practical reasons here. And as here, let's talk to people learn at CERN here at proton simulations. They use so far only classical simulations.
Yeah.
Okay.
Yeah, so there's work, and as one of the slides I skipped, actually, there's work that's been done on one-dimensional systems to look at how one can go from initial states to final states with fragmentation. Right, so that's one of the objectives that one would like to tackle for 100G physics. It's the inclusion of quantum coherence in the actual fragmentation process is something that is not included in the classical simulations. Is the phenomenological tuning is remarkable, but there's still pieces missing. And it was actually shown in this work by Christian Bauer and collaborators how when setting up the classical computation and comparing with the quantum computation, there's noticeable differences in the result due to quantum coherence and entanglement. So yeah, it's too early to be implemented, other than sort of hand-wavingly at the moment.
Okay.
Sorry.
I follow your argument, I mean, to learn something more, but people works on chemistry.
Yeah. Yeah, so chemistry has been a target for many more years than HEP and NP. So they are more sophisticated in understanding their problems and the quantum resource requirements for actually getting to their targets. So that's something that our community is working on, but we're behind. Yeah.
Okay.
Thank you so much here.
Yeah, my pleasure. Yep. Thank you.
Other questions from the audience? Well, let me interject another question of mine. At the beginning, you were talking about those two breakthroughs, and one of them is quantum computing, the other is artificial intelligence. Is there any potential synergy of the two where even more progress could be done?
Absolutely. So there's a large and almost exponentially growing literature on quantum machine learning, where you bring the two together, and you use the new features from both. I have no expertise or understanding of that, so I don't want to say much more, but that's certainly an area that people are actively working on. Yeah.
Right. Okay. Thanks. I don't see any other questions right now, so let me use this moment and thank our speaker, Martin, again for a very nice presentation and taking time to answer the questions.